Hi again. Let's talk about organic chemistry reactions. And we're going to begin by discussing them in general terms. We're just going to put them in categories. So the reactions I'm going to present here are not ones you have to memorize yet. We're just showing them as examples to get the category names understood. Okay? All right. So we're in Key Concepts, Unit 2, Part 1. Talking about different ways to classify reactions. And there's two general methods on how we can classify all the different types of organic chemistry reactions. Here's the first way. They're according to reactants and products. We kind of look at them that way. So first category is called an addition reaction. And that just means take two things, two or more reactants, and put them together. Combine them to create a single product. So we're just squeezing all the atoms to form one big molecule. That's an addition reaction. So we're going to look at the organic chemist's way of writing reactions. So here's an organic molecule, right? Something that contains carbon. That's how we define organic chemistry in the science world. And the organic chemist says, hey, I want to know what happens to the molecules that possess carbon. All the other molecules are just details. So on the left side are reagent, or reactant, however you want to classify the molecule on the left of the arrow, contains carbon. And then the other molecule, in this case, I'm just going to choose hydrobromic acid. That's the other reagent, but I'm putting it over the arrow, or you could put it below. We're saying, hey, what happens to the organic molecule when it mixes with HBr? Well, an addition reaction occurs. So you keep all the atoms from the organic molecule, right? There's 2 C's and 4 H's. They're still there. But the pattern that happens with HBr and an alkene, right? Guys, remember your functional groups, carbon-carbon double bonds are alkenes. The pattern is the pi bond goes away. Or in other words, the double bond becomes a single bond. And now, wait, these carbon atoms only have 3 bonds each. They should bond 4 times. Yeah, the atoms of H and Br go to those carbons. And in short, all the atoms that were found in the reagents, the H and the Br and all the C's and H's, they all combine to form one product. Cool, that's an example of an addition reaction. Let's look at elimination. Okay, it's kind of the opposite. Start with a molecule and have a reaction where you kick out more products, 2 or more products. And in this case, you might ask, well, wait, if this molecule is just going to spontaneously fall apart, is it really a stable thing to begin with? Well, we'll be a little loose with our counting of molecules. And it's okay to put in a catalyst or to heat things up. We're not going to consider catalyst and heat part of these reactants when we're counting things. So here's an example of an elimination reaction. Let's just show all the groups here. So I know I could have drawn a skeletal drawing. That was made things go faster. But I kind of want to just highlight all the bonds, just kind of keep track of the changes. Oh, the other thing, let's introduce another idea or reintroduce an idea. The reaction I picked for addition was a one-way reaction, a complete reaction. Technically, all reactions are equilibrium reactions, but this one goes really well in the forward direction. This other reaction, though, depending on concentrations, you can actually decide whether you want the reaction to flow to the left or to the right. It's a back and forth reaction, equilibrium reaction, goes by different names. But there are carbon atoms in these molecules, so now it's an organic reaction, an equilibrium reaction, if you will. Okay, let's add an acid catalyst. That's going to help the reaction proceed. Speeds, right? Catalysts speed up reactions without being consumed or used up. So add an acid to this alcohol. This is actually the alcohol found in beer and wine. So add an acid to it, maybe even heat it up. And what will happen is you eliminate a water molecule. Let's change the pink color here. An H and an OH will combine to form water. And so remember, the organic chemist is concerned about the organic molecule. So from the point of view of this organic molecule, it eliminated a water molecule. It eliminated H and OH. And what was left over? Well, 2 C's and 4 H's. 2 C's, 4 H's. Wait, I thought carbon needed 4 bonds. It does. You create a double bond. So you actually can synthesize or create alkenes from alcohols using an acid catalyst. Okay, that's a reaction we'll get to when we talk about reactions of the alcohol functional group. Today, we're just using this as an example to understand what is an elimination reaction. And what is it? Well, you start with one molecule and you split it into 2 or more. All right. I'm sort of a numbers guy. So you might summarize addition as 2 things becoming 1. Elimination is where you have 1 thing becoming 2 or more. So what's another pattern? Well, if we start with 2 things and make them into 2 other things, that's substitution. You have 2 reactants. They're just going to swap atoms, maybe functional groups, and then you create 2 new molecules. Well, we can shrink this back down, give myself a little more room. As an example, it's a very common example. This reaction is actually important in metabolism or digestion. So not this specific molecule, but the type of reaction. What's the name of this thing here? C double bond O with an O attached to a C. That's an ester. And so esters are found in fats, fatty acids, not fatty acids, but fats and oils that we find in our diet. And we can break those down by adding water. And so I'm doing a little bit differently here. I'm trying to highlight the fact that there's 2 reactants. So I'm choosing to kind of deviate from the organic chemist way of doing things. Normally we put this water molecule over or below the arrow to indicate, hey, there's no carbon here. The organic chemist just doesn't care too much about this. We're really focusing on the molecule with the carbon. But, right, we're highlighting the fact we have 2 things. So 1, 2. And we're actually going to use an acid catalyst again. That's pretty common, so we might abbreviate acid cat, meow, for catalyst. And what's going to happen? Well, you know what? I want to write or draw that water molecule so we can actually see bonds. We're going to exchange atoms, so I want to actually highlight some atoms. So let's redo this one. Sorry for those of you who are taking your notes in pen. Sorry. There we go. There's a water molecule. And how did I do this in my notes? I actually drew it the other way. That's right. We have a sort of like an alcohol group. Kind of. It's an OH group, but an alcohol group is supposed to be attached to a carbon. And this OH groups could attach to hydrogen, so not really. Oh, wait, I'm doing something wrong. I circled the ester group. So let's do it this way. Circle the OH group, circle the OCH3 group. And those are the 2 things that are going to swap places. And ooh, those are not curved arrows. I know they look like them. Organic chemists reserve curved arrows for showing mechanisms, for showing electrons moving to break or make bonds. Here I'm just trying to emphasize, hey, let's do a substitution reaction. Take this OH group, put it over here, and to make room for it, take the O and CH3 group, put it over here. What does that do? Well, you don't have an ester anymore, that's for sure. So we're going to keep the CH3 and the C double bond O. And we're going to bring over the OH group. Those are going to be the two atoms the water molecule is going to exchange. So now we have an OH over here. And then the O oxygen with the methyl group, that's going to come over here and attach to the hydrogen. So maybe I'll attach it this way. Okay, so there's a couple of different ways you can draw this molecule. This is methanol. It's got an OH group. This is an alcohol functional group. And what's the name of this thing? It's carboxylic acid, yeah. Okay, so we definitely made two new molecules. We did not lose atoms along the way. Nothing was eliminated. We didn't merge all these atoms and form one big molecule. No, we still started with two molecules, ended with two molecules. That is a characteristic of a substitution reaction. Nice. There's one more general category for organic reactions, and that's rearrangement. And again, if we kind of take the numbers approach here, what's our pattern? Addition was where you take two molecules, make one. Eliminations where you start with one, make two. Substitutions where you start with two and end with two. So what other combination is there? Well, if you start with one and end up with one, that's rearrangement. You start with one molecule and you just move some atoms around to make a new molecule. And again, you don't lose atoms along the way. Don't eliminate, don't bring in any new atoms. So as an example, I went to biochemistry, to biology. So let's bring in a phosphate group. So you remember the polyatomic ion, phosphate, PO4 3-. Okay, but let's actually attach one of those oxygens to a carbon and make it into an organic molecule. So there's a lot of molecules in our body. DNA, for example, has phosphate groups. Okay, so we're going to start with this molecule. And then we're going to use a catalyst, not an acid catalyst this time, but an enzyme. One of nature's catalysts, naturally occurring catalysts. Enzymes are actually huge proteins. They're incredibly powerful and very selective, very efficient. Yes, basically chemists are envious of these special catalysts. We like to try and make our own, but nature, she sets the bar high. These are pretty difficult molecules, enzymes. Okay, so take this enzyme and it can do a rearrangement. It can move groups around. So what does it do in this specific case? Well, it leaves a phosphate group alone. So attached to this carbon, that's primary. If you want a word to label this. There we go. Okay. So this is quite remarkable, actually. So what's the name of this functional group over here? The C-double bond O attached to two C's. Yep, that's a ketone. And what became of this carbon? Well, now it's part of the alcohol group. And not just any alcohol, it's a chirality center. This carbon is attached to 4 different groups, right? The H, the OH, aldehyde. Yep, that's an aldehyde. And then the rest of the molecule. So this enzyme is pretty cool. This molecule is achiral. There are no chirality centers. It actually transformed a ketone into alcohol. That's pretty cool. And then it did it stereospecifically. It didn't make a mixture of alcohols where sometimes OH is on a wedge, sometimes on dash. It did it specifically. Dang, that's awesome. And then along the way, there's an alcohol group that was at the end of the chain that got oxidized. Well, we'll talk about that in a second. It got changed into an aldehyde group. So it's like 3 huge things happening with one catalyst, nature's catalyst. Very cool. Okay, wait, that's not a reaction you need to memorize. Just kind of awe and respect. Ooh, isn't that cool? It's just there to illustrate, oh, this is a rearrangement reaction. You start with one organic molecule, you end it with one organic molecule. And if you count up the count up the atoms, write the chemical formula. These are isomers of each other. They have the same chemical formula, but they're different molecules. And that enzyme, for a pretty powerful enzyme, actually conducted that rearrangement. All right, so in the future, for this rest of this 1 year sequence of organic chemistry, every reaction that you will encounter can be put into one of these 4 categories. Sometimes it's not a nice clean fit, but we should be able to pick one of them, the best match all the reactions in the future. And that's not a task you're going to have to do necessarily on all your exams. However, when we start discussing new reactions, it's helpful to kind of see the pattern. And we're going to have to remember these reactions, and remembering patterns is a good way to remember things. So as you might see some crazy reaction, what the heck's going on? Well, just see which category it fits into, and that's one way to start understanding it. So this should be helpful, I hope. Okay, and then, you know, chemistry outlines these guidelines. Ooh, 4 categories. 4 and only 4? Not so much. We have exceptions. Oh, chemistry. Okay. Just to simplify things, yes, on an exam, if I ask you to categorize one of the reactions I present, it will fit into one of these 4. However, you may choose to categorize that reaction into 2 other categories. Things you're more familiar with, perhaps. Acid-base reactions and redox or oxidation-reduction reactions. So yeah, here we go. So in our key concepts, there's a notation that there are 2 alternate categories or terms that are permissible. I would strongly encourage you, though, not to use these 2 on an exam. If I ask you to classify, I am looking for one of the other 4. Okay, however, I can still give you full credit if you correctly use these categories. So acid-base, let's see an example of that. Well, in an acid and in organic chemistry, we got carboxylic acids. So I'll just go straight skeletal drawing, right? C-double bond O with an OH is a carboxylic acid. Oh, yeah, and I also put on the aromatic ring, the arene, the benzene ring. That functional group goes by several names. And then there's my acid. Let's add a very common base. Back in Gen Chem, we said sodium hydroxide all the time. And now, maybe on the exam, I might ask you to predict this product. That's from general chemistry. I know there's C's, it's organic too, but hopefully you would see this as, you'd go, okay, I know my functional groups. This hydrogen is part of a carboxylic acid. Hydroxide ion is your base. So therefore, mixing these 2 molecules will result in an acid-base reaction. The way I kind of predict products is I first define them. Here's my acid, H plus donor. That's my definition of acid. And here's my base, H plus acceptor. So do that. Hey, hydroxide ion, accept an H. So oxygen, as hydroxide ion, has 1 H and it gets another one. That makes water. An OH group with accepting an H plus, that's a neutralization reaction. You get neutral water. What happened to the acid? Well, it donated. So just copy the molecule without that H. Okay, that's not too satisfying. That's not going to give you full credit. What's wrong with this oxygen? Well, if we go back to the common patterns for bonding, oxygen prefers 2 bonds. I'm only giving it 1. How do you reconcile that? Well, go back to your definition. This neutral molecule releases an H plus. The neutral molecule creates something with positive charge. So you have to balance the charge. The remaining piece must be negative. Cool. We're almost done. I might accept this for full credit, but a better answer is, what became of the Na? Is it still stuck to the oxygen? No. Hydroxide ion was negative. Sodium is positive. Sodium is just a spectator ion. It follows a charge. This oxygen that used to be hydroxide ion is no longer charged. So no, sodium's like, forget you. Where's the negative charge? Over here. So sodium's over here now. Cool. Okay, that's acid-base reaction. What other type of reaction is this? Is this an addition reaction? A elimination reaction? Substitution? Or rearrangement? We start with 2 molecules, carboxylic acid and base, and we ended up with 2 molecules. Ooh, what was the pattern? Those 2 goes to 2? Substitution. Cool. This is actually an acid-base reaction, but you can also classify it as substitution. And that's actually the answer I was looking for on the exam. If I say classify this, I will give you full credit for acid-base, but I was looking for substitution. What was substituted? The H and the Na got swapped. Na went over to the O, the H went over to the hydroxide. Okay, now be a little careful. You might say, oh, I just have to remember acid bases are always substitution. Are they? Let's start with this molecule. What's the functional group here? Nitrogen with all single bonds, no double bond O next door. That's an amine. And then let's add hydrochloric acid. Ooh, what's the name of this molecule? Hydrochloric acid. You might remember from general chemistry that the amines, you may not have called them that. You may have called them compounds of nitrogen in general chemistry. But if we swap out the methyl with a hydrogen, then that's ammonia. And ammonia, you might remember from general chemistry, is a weak base. And it turns out the amines are also weak bases. Okay, so when we get to the section about amines, we'll talk about acid-base chemistry of amines. Amines are bases, weak bases. Ooh, hydrochloric acid's an acid. Do acid-base chemistry. Hey, amine, you're a base, so accept H+. Okay, so nitrogen says fine. That reminds me of the ammonium ion. Nitrogen can make 4 bonds. So H+, you go over here on the nitrogen. And when you do that, nitrogen's not doing honk normally. You know, HONC means nitrogen should be making 3 bonds. It's making 4. That's permissible. Nature says fine, but nitrogen, you carry a formal +1 charge. And then chlorine, you release H+. This molecule used to be neutral, but something positive left, leaving the remaining thing negative. And there's 2 ways you can draw the resulting product. You could say, hey, I'm showing all my bonds. Nitrogen's actually making 5 bonds, 4 covalent bonds, and 1 ionic bond. Ooh. This is 1 molecule. So what's the name of this? What's category of this molecule? Is it addition, elimination, substitution, or rearrangement? Well, 2 molecules become 1. Wait, that's addition. Yeah. So this acid-base reaction is not substitution. Turns out it's addition. All righty. Here's a harder one. Let's try and classify this oxidation reduction reaction. I had to go into 2nd semester organic chemistry to find something I liked. So let's start with this molecule, phenol or phenyl, however you want to pronounce it, alcohol group attached to the benzene ring. And then we'll use this molecule, That's sodium to chromium, so maybe dichromate. Sodium dichromate. Don't forget your polyatomic ions. We're going to keep seeing those. So review those. So if you need the name of this, sodium dichromate. That's an oxidizing agent. You might suspect that because, dang, look at all those oxygens. So it's an oxidizer. What does that mean? It's going to remove electrons, oxidizers. You know, oxidation is loss of electrons, so we're going to lose some electrons here. Sometimes the molecule will then also gain an oxygen atom, and that's actually what happens here. Okay, I wrote this this reaction like an organic chemist. I'm focusing only on the organic molecules. I didn't give any solvents. There might be some other catalyst here. There's not. But I didn't indicate the solvent. That's definitely here. Where does extra oxygen come from? Probably came from dichromate, but maybe it came from water. I'm not specifying that. I don't care. As an organic chemist, what became of my organic molecule? It turned into this one. And this is not a balanced equation, right? And that's the other thing organic chemists rarely do, except in their lab reports. We usually don't balance. So where's the sodium? Where's the chromium? I don't care. And then I want you to classify it. Dang. Okay. So then you might say, well, it can't be addition because the chromiums didn't show up here. So addition's where you merge all these reagents, make one big molecule. No. Okay. Is it elimination? No. Elimination starts with the first molecule and you make a smaller molecule because something here gets kicked out. So no, this molecule actually gained an oxygen. They didn't just simply eliminate. Okay, so it's not addition, it's not elimination. Well, is it substitution or rearrangement? Let's try rearrangement. Are there the same number of atoms before and after? No, there's an extra oxygen. So this can't be rearrangement. So it must be substitution. Well, what's being substituted? Well, we're going to take away this H here. We also have to take away the H here. Remember skeletal drawings? Okay, this carbon down here is only making, I only see 3 lines, a double bond to the left and a single to the right. There's an unwritten hydrogen there. So I'm gonna draw it in there. Yeah, so these H's are being removed and a pi bond's coming in here and an O is coming in here. So we're taking out 2 H's and bringing in an oxygen. We're substituting. That was a little trickier, but still doable. You might say, wait, I remember doing this and I remember oxidizing agents. I'm just going to guess it's a redox reaction, and that's how I will classify it. So that could get you points on the exam too, but then you really have to know your redox reactions. Anywho, this is better classified as substitution. Okay, ask me more in the discussion board or through office hours, student hours. That's one way to classify things: addition, elimination, substitution, rearrangement. There's another scheme, another way to classify reactions. So this one is, we're still going to use this. It's not as snazzy, so I don't use this as much. That's why I kind of made it secondary, but we are going to use this. Okay, here's a different way to classify reactions. Start all over. We can actually go back if we wanted to and look at all those reactions we presented and reclassify them by this method. And then this method, this classification scheme talks about how the reactions took place. One way they could take place is, well, when you're making reactants turn into products, how do you break those bonds? Do you break them homolytically? What the heck is that? Well, homolytically, let's say this is an incomplete chemical reaction. We're just going to take the Br2 molecule, and then let's say that's involved in a chemical reaction, and maybe the first step of the mechanism would be, let's break this bond homolytically. What does that mean? Well, what's one line? That's a covalent bond. How many electrons are in a covalent bond? 2. One line equals 2 dots in a Lewis dot structure. And so if we split the covalent bond in half equally, homolytically, equal halves, then 2 electrons separate. And what we'll show in our mechanism is that of these 2 electrons, 1 electron heads to the left and the other electron heads to the right. And afterwards, you're going to have 1 electron on bromine and the other electron on the other bromine. To be quite formal, we're not using full arrowheads. So a curved arrow usually has 2 barbs on it. We're going to use that type of arrow when we say 2 electrons are moving. Here, we have 1 electron moving left, 1 electron moving right. So we use a single barbed arrow. It's also called a fish hook arrow. Anyways, just showing you a few tools that we're going to use in organic chemistry. Okay, so then there's more steps that are involved here. These are not the final products. These go and react with probably the organic molecule. And afterwards, we're all done. We say, well, what kind of reaction is this? Well, what's really cool is that the bonds are breaking in half homolytically. So we could classify this reaction as a free radical reaction. That's what this is, a species with an unpaired electron. Where do I have that? Reactive, there we go. Radicals are reactive as they attempt to pair up the unpaired electron. They actually have no charge, they're neutral. If you count up all the protons and all the electrons, they balance. So there's no net charge here. You may have seen free radicals before, but this is a radical reaction because we split the bond in half homolytically and made radicals along the way. These are not the final products, they are intermediates. So maybe in general chemistry, hopefully in general chemistry, you talked about catalysts and intermediates before. So they're coming back. Okay, so that's one way to classify the reaction under the second scheme. There's another way you can break that bond, and that's an unequal bond separation. You can break it heterolytically, unequally. So how does that happen? Well, 1 line equals 2 dots, and just those 2 dots, those 2 electrons, just all go to one of the bromines. So now the first bromine is missing a bond, so now it's positively charged. The second bromine gained a lone pair, and so now it's negatively charged. And then we keep moving forward, and these 2 bromines may react further to complete the reaction. So I'm not showing the full chemical reaction, just the start of one. But here's the key step. When we break the bond, we broke it heterolytically, and we made ions, not radicals. Radicals are neutral, and they have unpaired electrons. Ions have charge, and they usually have pairs of electrons. All right, maybe I should have shown that. Let's draw the full Lewis dot structure of Br2, elemental bromine. All right, so now everybody has 8 electrons. They can see 8 electrons. So afterwards, this bromine only has 3 lone pairs. This bromine has 4. This one doesn't have an octet. That's not stable. This one is stable. So it turns out this is the most reactive piece that's going to go on and do something cool. What else do you need? Oh, what's this class? How do we classify this? It's called a polar reaction. When I think of a polar bear, I think of bears that live up in the North Pole, not the South Pole, separate ends of the Earth. These molecules, these species are separate charges, plus and minus, they're opposite. So that's where the term comes from. Polar means they're separating. All right, so now we have 2 types of reactions. Free radical form single dots, single electrons, or polar reactions. Pairs of electrons, and we have charges. Is that it? No, there's one more way. One more way you could do a chemical reaction is that where you break a bond and you immediately make it. So you never get a radical and you never get an ion. Those are kind of rare, but they do happen. and they're called pericyclic reactions. And as an example, we got this reaction we'll see at the end of this semester called the Diels-Alder reaction. It's really cool. So take 4 carbons containing 2 alkenes, and take another alkene, and you heat these up. And in one step, you actually make cyclohexene, a cyclohexane molecule with an alkene. Very cool. And then we haven't shown the mechanism, but it turns out they just merge together, and you have to break some pi bonds, right? So you have to break some bonds, but you also form new bonds. This carbon has to connect to this carbon connects to that carbon to close up the ring. And it all happens in one fast step. It's really cool. All right, so the second classification method has 3 categories. Radical reactions, come on, there we go. Radical reactions, number 1, polar reactions, number 2, and pericyclic reactions, number 3. Oh, if you want to go back to the first method of categorizing, what kind of reaction is this, where 2 molecules become 1? Yeah, this is also an addition reaction. So depending on how you want to classify it, the first method, you call it addition. Second method, you call it a pericyclic reaction. Okay, again, you don't have to memorize these. This is just different ways of classifying reactions. The first method, addition, elimination, substitution, rearrangement. Ooh, gotta have those memorized. The more you say it, the better you get it. That's the best method. That's the one that's most commonly used. However, as we see new reactions, we're also going to classify them this way too, so we can better understand them. Let's see. I think I already said this, but it doesn't hurt to repeat it. The main difference between the 2 methods, first method, addition, substitution, elimination, rearrangement, we are assigning categories based on the numbers of reactants and the numbers of products. The second method, radical reactions, polar reactions, pericyclic reactions, that method is based on how the reaction happens, the reaction mechanism. And if you hadn't heard that before, we'll see lots of mechanisms. That's a step-by-step process where you break old bonds in the reactants, and then you make new bonds to turn them into products. And we need to show that in a reaction mechanism, step by step. How do you make these reactants turn into products in great detail? And it actually involves a lot of understanding, and it's very insightful and actually quite powerful. That's coming later. All right, let's simplify this further. It turns out, using the second method, radical reactions, polar reactions, pericyclic, most of the reactions we'll see are polar reactions. We're going to have intermediates show up having charge, pluses and minuses. Okay, so knowing that, that's helpful to help us understand the reactions, and it's also helpful for us to predict the products. Most of these reactions are going to involve charges, pluses and minuses. Okay, so as you look at your reagents then, they usually come in with some slight positive charges or partial positive charges. And so now we're going to say, hey, here's one reagent with a slight positive charge. Here's another reagent with a slight negative charge. Hey, opposites attract. That's how we can predict the reaction occurring. And we got new terms. Scientists love new terms and every new idea. So the molecule possessing a positive charge is called a nucleophile. No, that's not right. How did I know? Because I try and make myself the nucleophile. I am the nucleophile. And what am I? I am a nucleophile. Phile means seeking or loving. So I'm seeking out the nucleus. The nucleus has positive charge. Why would I seek the positively charged nucleus? Only if I'm negative. So there you go. So the molecule that wants positive charge is itself usually negative. It's got to at least have a lone pair of electrons. Not lone pair. It needs to have a pair of electrons. Sorry, I'll show you an example of nucleophiles in a minute. A lot of these are Lewis bases, electron pair donors. The other molecule, right, So the nucleophile is the molecule seeking a positively charged thing. Well, the other thing, it has the positive charge. So now be the electrophile. I am an electrophile. Phile means seeking or loving. Why do I love electrons if I'm an electrophile? Because I have positive charge. I'm attracted to something negative. So the electrophile are those molecules or reactants that are seeking electrons or something with a slight negative charge. They themselves usually carry a positive charge, but it's true they can have no charge. And they typically are Lewis acids, electron pair acceptors. Hey, they're seeking electrons so they can accept them. Lewis acids. And of these two terms, we use nucleophiles much more often. Cool. Okay, electrophiles, nucleophiles. Let's explore those two terms in a little more detail. I think I have to go to the right. Yeah, and then up. And more right. There we go. Okay, so as we discussed nucleophiles and electrophiles, let's also introduce a new tool. You don't see it too often, but there are a few homework problems that show this, and there's some great websites that describe organic chemistry, and they use these electrostatic potential maps also. Another tool, if you will, and the idea is that we're going to color code the surrounding region around these molecules. So this is a carbon with a chlorine and carbon. And if we color code them red, it means they're red hot and active with lots of electrons. If they're blue, they're cold, they don't have electrons, they're usually positive. And so if you go to the periodic table and ask, who's more electronegative, chlorine or carbon? The answer is chlorine. It's closer to fluorine. It's more electronegative, which means this bond is actually a polar covalent bond. Those two electrons are actually drawn towards the chlorine, starting to make it negative. Carbon then isn't seeing those electrons, so it starts, hey, you're taking away my jacket, my cold, yeah, I'm feeling cold, whatever. It's starting to feel a little blue, so you have some blue hues here and some red hues there. And the richer color in red will emphasize there's a greater charge separation. Over here, we have carbon attached to lithium. And there's some, and I know lithium is a metal. It's on the left side of the periodic table. Carbon is a non-metal. Back in general chemistry, we would predict a metal with a non-metal should make an ionic bond. So there is some ionic property here. It turns out, though, you do some careful measurements and careful reactions, this bond actually behaves more like a covalent bond. So again, more exceptions. So this molecule exists. It's very reactive. Why is it reactive? Because lithium's a metal. It likes to release electrons. Carbon's more electronegative than lithium. So it's gaining electrons and it's building up negative charge. And that's where the reactivity comes in. Carbon is not that electronegative. Why is it building up negative charge? Well, lithium is forcing it to. And carbon's just not happy with that. This molecule is extremely reactive. It'll catch fire with water. So we're not going to play around with that molecule, methyl lithium. But anyways, I just want to show you the color coding. Look how blue this is, and look how much redder this is than the other one. That gives you a sense that there's greater charge separation here, and maybe greater reactivity. Talked about acids and bases. Thought I'd just throw this in there because it's cool color scheme. There's a little red region here. Those are the lone pairs on oxygen. If you have an acid, maybe the state Cl, the A could be chlorine. Hydrogen goes over here, and now this oxygen that was slightly negative because of electronegativity now makes 3 bonds. Oxygen now carries a positive charge. So now the positively charged oxygen is electron deficient. It's positive, not negative, slightly negative. And so you see all this blue color. Oxygen is still more electronegative than carbon. So it's yanking on these electrons, pulling them up towards the oxygen. And that's making carbon slightly positive. And so now the whole molecule. And then carbon's doing the same thing to these poor hydrogens, saying, help, I'm losing my electrons, I'm slightly positive. And these bonding electrons are then attracted to the slight positive charge. And now the hydrogens are feeling a little positive too. The little molecule is slightly positive. And now this molecule doesn't have many electrons, it's going to go seek them. So you could classify this whole molecule as an electrophile. So let's go find some electrons because it needs some. Okay, last thing about nucleophiles and electrophiles, some examples. Here's the proper curved arrow saying, hey, if you have this molecule with a lone pair, this molecule missing a bond or has a positive charge, the lone pair can be used to connect these atoms together. And so we're going to show the flow of electrons with the curved arrow. Lone pair connects to the A, atom A, and make a covalent bond. These electrons are donated. You can also say, hey, molecule B here is a nucleophile seeking that positive charge. And then if you're over here, you can say, hey, molecule A is seeking this lone pair. It's an electrophile. Now, because our curved arrows start on electrons and move towards the other molecule, we usually focus on the nucleophile. That's where we're going to begin our curved arrow. That's where we're going to begin our mechanism, how we explain how these two things react to form products. So here's some more examples. Let's start on the bottom row. Again, because nucleophiles are usually how we're going to describe these reactions. So we have something, Nu for nucleophile. We're not even saying what the molecule is. Somewhere in this molecule, there's a lone pair. It's going to connect to this carbon. That's also a cation. Yeah, the name of that is carbocation. Carbon making 3 bonds, positive charge. The nucleophile will attack it and make a new bond to the carbon, give it 4 bonds, and do an addition reaction here. Connect the 2 together. Here's a substitution reaction. The nucleophile can use its lone pair to connect to the carbon, and the halide, halogen, can break this bond and go away as a negative anion. You might remember chloride ions, fluoride ions, bromide ions, they're stable as negative ions, so that's a reaction that's favorable, and this would substitute the nucleophile for the halogen. You're going to have this acid-base reaction happen. H plus will donate to the nucleophile. Both our curved arrows are showing the lone pair connects to the H, and hydrogen can only make 1 bond, so this other bond has to break and turn into a lone pair on the oxygen. And then finally, here's another common scheme we'll see next semester a lot. Aldehydes and ketones have a C double bond O, so do esters. Nucleophiles can attack that carbon. Why? Why is this lone pair seeking positive charge? Because oxygen is more electronegative. And I would say that the pi bond gets bumped up onto oxygen. So lone pair connects to the carbon, loses the pi bond, becomes a new lone pair on the oxygen. Anyways, you don't have to memorize any of these patterns. It's just helping you see the use of curved arrows and identifying nucleophiles. You can do the same thing with electrophiles, but again, that's less common. So if you have questions about that, you can ask during the student hours. And then your key concepts. I got this note, which I've already mentioned a couple times. Halides are more electronegative than carbon. So knowing that, you can assign the halide a slight negative charge, delta minus, and the carbon then is a slight positive charge. You can look at the other reagent, look for positive and negative charges there, polar covalent bonds, maybe find a lone pair, and then that'll help you predict the product. You'd say, okay, the one molecule has a slight negative charge or a lone pair of electrons, which are negative. It'll be attracted to this slight positive carbon. Hey, maybe that's where the reaction occurs. Opposites attract. So that's a great way to predict reactions. Nice. Okay, what else we got? Let's see, I don't think anything else down below. Go back up and over. Okay, let's end this video with a very common reaction in organic chemistry. This one goes through a radical mechanism, meaning along the way, we're going to make intermediates with unpaired electrons. So you can classify it as a free radical or radical reaction. The second classification method, it's a radical reaction. It's also a substitution reaction. So one example of this type of reaction is methane. Reacts with chlorine, and a hydrogen and a chlorine will swap places, be substituted. to form this molecule, chloromethane and hydrochloric acid. So there you go. This is a substitution reaction. It's also a radical reaction, depending on how you want to classify it. More later on this, but yeah, now this reaction could be on your next exam. But it's more important to understand the pattern, right? So on your next exam, exam 2, I may not put methane. I may put a different organic molecule. And it's up to you to figure out what the products are. And it's like, wait, you didn't talk about that reaction. You only talked about methane. Well, it's a pattern that's important. So what is the pattern? Substitution. Take away an H, put on a Cl. So now it doesn't matter what I give you here. You know the pattern. Take away an H, put on a Cl if it's Cl2. Cool. So that's powerful. So memorize patterns rather than specific reactions. Don't memorize methane with chlorine makes chloromethane. Got it. No, memorize the pattern. It's substitution. Take away an H, put in a Cl. We're also going to talk about the step-by-step process to get there. We'll talk about the reaction mechanism. Cool. Okay. Let's just go in order because there's several details here. First of all, we're going to talk about this reaction because it's a great introduction to understanding how to do a reaction mechanism. This mechanism, the step-by-step process, is really well understood, more so than a lot of other organic reactions. The danger here for some students is they think, ooh, I know this really, really well. I'll apply this mechanism to everything. No, this is a radical mechanism. Most reactions are polar. They go by a different mechanism. So keep these separate. Cool. The other danger is that, ooh, we know this really, really well. So every time I need to use my own reaction, or Dennis says, choose a reaction to do here. A lot of students pick this one. Ooh, it's not a good one. So I just, right from the get-go, just saying, hey, this is a nice reaction to understand mechanisms, but it's not a good method for making molecules with halides on alkanes. Why? Because you get mixtures of products. So I know this is the overall reaction. This is like the major product. So if you mix 1 mole of methane and 1 mole of chlorine, you don't get 1 mole of this. I know that's the balance equation, but your percent yield is not going to be 100% this. The reason for that is as the reaction gets started, you start making that chloromethane, and it's still in the same beaker as these two things. So now sometimes the product will react with your reagent. And so this molecule reacts with Cl2 and you do substitution again. What substitution? That's where you take off this H and add a chlorine. And now this molecule is still in the same beaker with these two. And so now this molecule sometimes reacts with Cl2. And you form this molecule, it turns out to be chloroform. Substitute again, and yeah, there's still a chance this last hydrogen could be substituted out too and form carbon tetrachloride. All right, so this is not a good reaction to do in the lab because you're going to make multiple products. And it gets even worse. That's just for methane. What if you start with butane? Well, now which hydrogen are you going to substitute? One of the primary ones, primary hydrogens at the ends? If you do, you make 1 bromobutane. But what about one of these hydrogens in the middle, the secondary hydrogens? You can do that too, and now you make 2 bromobutane. So now you're making mixtures again. I would also say that these are the mono-substituted products. There's only 1 bromine on these molecules, mono meaning 1. This molecule has been di-substituted. It's a di-substituted product. Why? Because there's 2 chlorines. So we start with methane and we remove 2 H's and put on 2 chlorines, di-substituted. Okay, so on a homework problem, I might say draw all the mono-substituted products. And yeah, in the laboratory, if you do this in the laboratory, mix butane with Br2. Oh, I didn't mention, you need a little heat or light to get the reaction going. Br2 and butane, you mix it together. Yeah, you'll make these 2 molecules, but then these molecules can also react with more Br2 and add more bromine, substitute more bromine onto these chains. and you'll make di-substituted products and tri-substituted products. And you can go all the way up to substituting all 10 hydrogens. No, no, no. Okay, I'm not going to ask you to draw all those. I'll just say, just give me the mono-substituted products. Show me all possible ways of putting one bromine on this molecule, mono-substituted. Nasty reaction, right? Okay. Why are we studying this? Because it's really well understood. It's a way to introduce mechanisms. So what do we need to know? If you see a halide, Cl2, with an alkane, the pattern is substitute one hydrogen with one chlorine, and I usually just say, just stop there. Just do mono substitution. It turns out you don't have to use just chlorine. You can use any halide. Well, not really. You can use bromine. Chlorine, bromine work fine. But in the laboratory, we have problems with these two. Fluorine is so reactive, it reacts with any container you put it in. So that makes it really difficult to get the reaction with the alkane. So we're just not going to use F2, fluorine gas. No. Super reactive, reacts with your containers. Iodine is the other end. It's pretty mild. It's really stable. It's not that reactive. Your yields are lousy. It doesn't react that well. So we're not going to use that either. So chlorine and bromine. That's your two choices. So I use bromine here. I use chlorine up there. Pattern's the same. Substitute a hydrogen with that halide. What else do we need to know? Yeah, any alkane can work. You do need heat or light, and the mechanisms is going to explain why. Why do you need heat or light? Well, we'll see in the step-by-step process of doing the reaction why heat or light is required. Already mentioned substitution. Ooh, and to get all your points on the exam, you have to list all the products. Well, I'll narrow it down. I'll say just list the mono-substituted products. And then just like in butane, you had to show all possible ways to put the bromine on. And the two possible ways, right? One bromobutane. You could have chose to put the bromine on this end, but that's still one bromobutane. Right? And there's the other molecules, two bromobutane. Yeah. And then there's the note here. Yeah, on exams, you'll be told whether it just had one. I might ask you to draw the dihalogenated products, the di-substituted products. And then you're looking at 2 halides per molecule. Memorize the mechanism. Did I mention that yet? Someone once told me organic chemistry is a memorization marathon. So go at a long pace, don't cram, don't sprint. Lots of memorize. Oh, I think that's it for the key concepts in terms of what's typed up. Yeah, okay. Well, let's see the mechanism then. Okay, so let's start with that reaction of methane. Let's write this as overall reaction. And we won't do it the organic chemist way. We won't put anything over the or above the arrow, over or below the arrow. I'll choose Cl2, but the mechanism works with Br2. Same pattern. I'm going to use methane, but you could use ethane, propane, butane, pentane, whatever ane, insane. You do need heat or light. H nu, Planck's constant times the frequency. 2 letters versus 5, Chem SY. This is another way to notate, oh, I'm gonna use light in this reaction. Or do a temperature change, delta for change. We're gonna add some heat. So you might see a little delta symbol, the Greek letter D, triangle, indicating, ooh, we're gonna heat this one. Nah, I'm gonna shine some probably UV light, high energy photons, H nu. And what's gonna happen? Substitution, and we'll stop with mono substitution. So 1 hydrogen comes off, 1 chlorine goes on. Well, let's balance it. What became with the 2 chlorines? 1 went to the alkane, the other one paired up with the hydrogen. Cool, that's the overall reaction. Let's do the mechanism. Step-by-step process of how methane and chlorine gas become chloromethane and hydrochloric acid. How does that happen? Well, there's 3 steps. And within the second step and the third step, there's multiple steps. Yikes, step within step. On the exam, you don't have to name these, but because it's so well understood, people, chemists, right? Every new idea gets a new label. We do have names for these steps. The first one's called initiation. Let's get the reaction started. That's where the heat or light comes in. So heat or light, sorry, that's light or heat. That extra energy from the photons, the light, or the extra energy from thermal energy, heating it up, is going to help break some of the chlorine molecules. Let's emphasize something else here. How do we do this reaction? How would we do this reaction in a lab? Would we get our molecular tweezers, pull one molecule of methane and put it in a big old beaker, and take one molecule of Cl2, shake it up, and get one molecule of, no, you don't. You just get a whole bunch. You get Avogadro's number, right? 6 times 10 to the 23rd of these things. Huge, huge number. So there's lots and lots of these molecules. You don't just have one of each. That's what's happening in the lab. So in the lab, you might have Avogadro's number of Cl2s, but a few of them, not all of them, some of them react with that extra heat. Most of them just bounce around, go crazy with the extra heat energy if it's heating it up. The light doesn't get absorbed by all the Cl2s, just some of them. And those few chlorine molecules, Cl2 molecules that absorb this light or absorb the heat and break this bond, break it homolytically, where one electron goes to one chlorine, the other electron goes to the other. Remember, single barbed arrows, fishhook arrows, mean movement of one electron. And so then you get 2 chlorine radicals. Well, I'm just going to put a big 2 in front instead of drawing the 2 Cls. This is the first step of the mechanism and explains why heat or light is required. You have to make these intermediates. Cool. Okay, what's next? Next step is propagation. What you do, the pattern is take your product, intermediate really, of the previous step and make it a reactant in your next. And that's going to react to something from the overall reaction. So there's Cl2 and methane. Some of the Cl2 split, but there's still Cl2 that didn't react with heat or light. So now you have a 50-50 shot. Which of these you want to put down here? Well, it helps knowing what the product is. How about this chlorine can somehow substitute into this methane molecule and make them chloromethane? Well, that's not this exact step, but at least it helps identify that the methane is coming in next. When you draw molecules, you decide how you want to draw them. So you don't have to draw it my way. I'm just choosing because when I'm drawing it, I get to pick. So instead of drawing all 4 bonds to the H's, I'm just going to highlight one of the carbon-hydrogen bonds. And I'm choosing, hey, this is the bond that's going to break homolytically also. So there's one line equals 2 dots. One electron is going to pair up with this electron of the free radical. So this bond breaks. The H travels over here with that one electron it took from the bond, pairs up with this one electron, and makes a molecule of hydrochloric acid. Hey, we just explained where one of the products comes from. It comes in the first propagation step. What became of that covalent bond? It split. One electron went to hydrogen, the other electron goes to carbon and creates a methyl radical. Cool. Okay, are we done? Is that our full mechanism? No, because CH3 is not a product. It's not even stable. Carbon needs 4 bonds, it only has 3. So you got to keep going. So what's the pattern? Well, for the initiation step, we took the Cl dot, Cl radical, made it a reactant. This is done. That's one of our products. So let's take the other thing that's not done, make that a reactant. Now let's react with something. Got 50-50 shot. Well, how are we making this chloromethane? Well, how about the methyl radical takes one of the chlorines from Cl2. So some of the Cl2 reacts in an initiation step, but most don't. Most of them react here in the second propagation step. Okay, what happens? This bond follows this pattern. Ooh, that's nice. Patterns repeat. So the bond breaks homolytically. One electron pairs up with this radical electron and makes a new covalent bond between the methane, sorry, that's not methane, this methyl group and the chlorine. So maybe I'll draw it this way. And that's this product right here. Yay, we just explained how that product showed up. What's left over? Well, the Cl2 molecules split homolytically, and on the right side, we make another chlorine radical. And that ends the propagation steps. There's just two. Now, if you could watch a movie of this reaction taking place, if you could see the molecules and reagents and intermediates actually bounce around in the beaker and doing their thing to make products, keep an eye on this chlorine. What becomes of it? It actually will repeat the first propagation step. So the chlorine radical will come over here and find a new methane molecule, make hydrochloric acid to create a new methyl radical. Then what becomes of the methyl radical? It'll go find another Cl2 molecule to form chloromethane and make another chlorine radical. And the chlorine radical goes back up here. This pattern repeats multiple times. In fact, in one study, for every one time that the initiation step takes place, so shine light in here and some of these react, well, every time one of the Cl2 molecules splits homolytically in the initiation step, this pair happens 5,000 times. So it's sort of like a chain reaction. Now that's not something you have to memorize. It just gives you some insight in this mechanism. So in the propagation steps are where the products are forming, hydrochloric acid and chloromethane. But this keeps going. And we're not going to do this part, but sometimes this molecule, chloromethane, will react in this propagation step. And now another chlorine will eventually add on, and you make a di-substitute compound. Okay, we don't want that. So it turns out there's ways of trying to stop it early. And that involves the third step, the termination step. And I should say termination steps. There's multiple ones. The pattern here is to quench or, get rid of the radicals. So what's really going on here? Well, as these molecules all bounce around in here, right? So let's start all over. Light comes in here, splits the chlorine into chlorine radicals. The radicals grab methane, make hydrochloric acid, another radical. That methyl radical grabs chlorine gas, makes a product by another radical, and then back and forth they go. These two propagation steps continue until one of two things. You run out of these molecules, in which case it start reacting with the other products, yikes. Or somehow the radicals react with each other. So as this happens, right, imagine a beaker with all these molecules just bouncing around. At the start of the reaction, before you added heat or light, you had pure methane and pure chlorine gas, a 50-50 mixture, let's say. Lots and lots of these molecules, Avogadro's numbers. Shining a little light, a few of these Cl2 split the radicals, and then lots of methane, lots of Cl2 jump into the propagation steps and starts cranking out products. And then these molecules are showing up all the time too. And eventually, just random chance, maybe these radicals collide with each other. And what does a radical do? They want to pair up their odd electron. So that's how we quench the radicals. We actually will observe pairing of all possible radicals as possible steps here. So as the reaction's happening, you're making a few chlorine radicals. Maybe two chlorine radicals see each other and collide. So one chlorine radical will combine with the chlorine radical, the electron of the other chlorine radical, and make a covalent bond between those two. Sometimes the chlorine radical will react. I should put a plus here. One reagent plus another reagent. Well, the second reagent might be a methyl radical, because that shows up too. Show my curved arrow, because this is the mechanism. Fish hooks, they combine. And all we're doing here is that these two dots kind of meet in the middle, connect to each other. Two dots form a pair, a covalent bond. And hey, we actually made product. That's the chloromethane. The first termination step made more Cl2. Yeah, maybe if you're still shining light, it could jump into the initiation step, or the Cl2 might jump into the propagation step here. But here's something unexpected. The other possibility is for two methyl groups to collide. Two methyl radicals. And it's getting a little crowded up here. You can still put your curved arrows up here. You can go underneath here too. Your choice when you're drawing the molecules. So if two methyl radicals collide, you create ethane. And it turns out if you go back in the lab, you can detect trace amounts of ethane. Okay, and so why don't we get a whole bunch of ethane forming? And that's because just of the kinetics of the reaction, the rates of reaction here, and the frequency of the reactions. So every time you shine light, every one time that event happens, the propagations happen about 5,000 times. And then on average, for every 5,000 times these propagations happen, one of these termination step will happen. And so you get like 5,000 times more methyl chloromethane and hydrochloric acid than ethane. So 5,000 times as much. Yeah, this is like a tiny, it's less than a, less than a point, what is that, 0.02%? Tiny amounts, trace amounts of ethane. Even less than that, because there's three termination steps. Okay, I think we finished the mechanism. Take-home features, yeah, memorization is what the key is. These terms can help you with the memorization process, right? So initiate means start making radicals. Propagation means crank out products. And we're switching, right? So the pattern here is a halide with an alkane makes hydrochloric acid and methyl radical. And then the carbon-based radical will react with the halide. So that's kind of a repeating pattern. Halide with carbon, carbon with halide. And then we make the other product with a halide radical. And then down here, termination. Go back and look at all your steps and find your radicals. Hey, here's a chlorine radical. Here's a chlorine radical. Here's a methyl radical. Here's a methyl radical. Here's a chlorine radical. There's only chlorine and methyl radicals. So find every combination to pair them up. And those are your termination steps. Cool. We've gone over quite a bit today. So let's take a break. Take care.